All right, hello everybody. My name is Laith Rabah, and along with Carson Warner, Stefan Gonzalez, and Anya Frohawk, we have been working on FRGB Instruments. The F standing for frequency based, and everyone else already knows what RGB stands for. We're sponsored by Professor Leinecker, and we're about to show you what our whole project is all about. So the problem we're trying to tackle is that musical performances, at least classical music and orchestras, haven't had much advancement in recent years, at least not as much as your typical hip hop artist or a rock band or a pop singer. So we're trying to remedy that by creating a more visual spectacle to go along with the performance, so it's not just something you're listening to, but also something you're witnessing and something that'll be different every time you watch. So our main three objectives are to visualize the sounds emitted from the instruments with RGB lights, whereas the lights would show different colors depending on what note you're hitting. And then we're going to process the frequency and the volume of the sounds through a microcontroller, which is a Raspberry Pi 4 in our case. And then we want to refine the program to make a smooth transition between the colors for each note so that it's a lot easier on the eyes and more appealing to look at. So in terms of specifications and requirements, we had a few more originally, but we just put our main ones in the slide. The first one being a minimum SNR value of 25 decibels, SNR being signal to noise ratio. Basically, the higher the decibel value of the SNR, the less background noise is picked up. So when you think of in terms of bands or orchestras, there's going to be a bunch of different instruments played at the same time. We want to minimize how much sound from these background instruments is played to more accurately represent the music being played with the colors. The next one is a minimum refresh speed for the program of 5 iterations per second. Thankfully, we've been able to pretty easily reach 10 iterations per second, I believe is what we're at right now. So we've been able to knock that one out of the park pretty easily. Next one is the low power mode. We want the system to go to sleep after 5 or 10 minutes of inactivity because we don't want to just consume power during breaks or rest periods or if they're just having a chat with the audience. Uh, the fourth one is portability. We want it to be easy to transport and lightweight to be more accessible to as many people or bands and orchestras or musical artists as possible. And lastly, we want the total cost to be under $1,000. Now, this was including instruments for testing originally. I believe right now our cost is around $200. So we've been able to stay well under this one.
Here we have the initial prototype that shows basic component layout and how each component is interacting with one another and how it will achieve the desired effect of lighting up the instrument. Our example instrument in our prototype is the flute. Here we have our hardware block diagram, which shows the relationship between all components and how they interact with each other. First audio signal is recorded into the microphone, which passes through the ADC converter and then fed to the Raspberry Pi. The Raspberry Pi then converts the audio to its respective color and brightness, outputting the information to the LED strips. The Raspberry Pi is also connected to an LCD screen display used to choose colors and themes for the LED strips. The Raspberry Pi is then powered by a wall power supply, which is passed through a DC to DC converter.
The software block diagram shows the process of interpreting audio from the microphone and processing it to output to the LED strips. First, the program asks the user to choose a color theme, and then the program will start processing audio input. The audio input passes through a Fourier transform to gather the frequency and volume information. After this, the frequency that is obtained from the microphone is then compared with a lookup table and then assigned to its respective color. The color is then sent to output to the LED strip.
This is our house quality graph. It has the requirements that our sponsor gave to us, as well as some target values for our different parts to meet. Initially starting this project, we began thinking about the software side of it as that was a large part of this project. Then we begin thinking about how we would make hardware to fit with the software, what would run the code the best, and what would create the least amount of noise in order to get a clear result. Next was to try to make it as portable as possible, as we are doing something that involves music. So a lot of musicians and stuff would like to go perform and everything. So we wanted to make that as easily as possible for them. And the next was to polish it by making an app for it so that they could easily select themes for different color schemes, like all blue or rainbow or something.
Now we're going to move along to our component selection. One of the first components that we chose was our microcontroller. The requirements for our microcontroller were that it needed to strike a balance between speed, price, specifications, I/O connectivity, and overall community support. Here we have our microcontroller comparison table, which shows the 3 microcontrollers and the pros and cons of each. First we have the Raspberry Pi 4, which costs $158, and out of the 3 microcontrollers is the middle of the ground in terms of speed. It has a variation in terms of RAM capacity and has all the I/O that we need. However, it is the largest microcontroller. Next up we have the Raspberry Pi 3, which is the cheapest out of the 3, and only costs $80. However, it is also the slowest. It only has 1 GB of RAM capacity, however it also has all the I/O that we do need. It is the second largest in terms of size. Finally, we have the NVIDIA Jetson Nano, which is the most expensive out of the 3, nearing $300. However, it is also the fastest, with 4 GB of RAM capacity. It is missing some I/O, but it is also the smallest microcontroller. Putting all of this into account, we went with the Raspberry Pi 4 due to its price to performance comparison and its overwhelming community support. The next component we chose was our microphone. Aside from the microcontroller, this is the most important component because it will be the main input that the microcontroller needs to interpret. The main requirements that we desired for the microphone was a balance of portability, polar patterns, and overall clarity. Here we have our microphone comparison table, which shows the 3 microphones that we chose for testing. First we have the shotgun microphone, which has a low bar picker pattern. This polar pattern is very direct and picks up audio in only the direction that the microphone is facing. The shotgun microphone is the middle of the pack in terms of cost. However, it is quite large and can only be mounted on a floor stand. Next we have the contact microphone, which has a direct connection to the instrument and picks up vibrations from contact alone, which lends it below average sound quality due to high frequencies being lost in this process. The contact microphone is the cheapest microphone and is the smallest. Next we have the clip-on microphone, which has a cardioid pickup pattern. This pickup pattern is very wide and can pick up audio from nearly 180 degrees of the facing of the microphone. The clip-on microphone is the most expensive out of the 3, however it is very small and has high fidelity quality. We chose the clip-on microphone due to all of these different aspects, as well as its small size and high fidelity.
When I began researching the ADC, the biggest factors that came up with different ADCs was latency, as we don't want much lag between when the sound comes in the system and the LEDs change colors. Size, because we want as much portability to the system as possible. Noise, because there's already going to be background noise coming in from the microphone. We don't want any added quantization noise, and we want to minimize the background noise as much as possible. Resolution, as this is an audio signal, so we want as much of the original signal in the output as possible. There were 5 structures we compared when looking to figure out how to design the ADC that we were building. The first one was the dual slope. While it would be small, it would be very slow to get the resolution that we wanted, as it had to find each bit one at a time. The flash, it has a lot of comparators, so it finds all the bits at the same time. However, you would need 2 to the n comparators in order to get that resolution that we needed. It would be an insane number. Pipeline, while it fixes the issues with the flash a little bit, and it would be very fast, however, it would still be a lot of comparators and would require a very big circuit. Delta Sigma, while it is on the slowest side, it deals with noise the best, as it does noise shaping, so it pushes all of the noise to higher frequencies, which is good for our case because we only care about the low frequencies. Humans can only hear up to 20 kilohertz. So we decided to go with the Delta Sigma ADC. This is our ADC schematic. So we have a op amp which has a difference amplifier as well as an integrator. The difference amplifier adds the output back into the input. Then we have it go through another set of op amps, which is the same thing, to make it a second order ADC. Then we go into a comparator so that it compares if it is greater than ground or not, and that gives either a 1 or a 0 to digitize the signal. That goes into a D flip-flop. The D flip-flop compares the signal in with a clock signal on the megahertz. This oversamples the signal. It then goes into a switch, which compares if it is greater than 0 or not. If it is greater than 0, it gives a 5 volts. If it's less than 0, it gives a negative 5 volts. That then goes to an inverting op amp and back into each of the original op amps in the beginning as a feedback loop. Then it goes to a decimation filter, and this takes it from the oversampling rate that we have it at in the megahertz down to a much reasonable value. This allows for the signal to be much clearer. This is the PCB layout of our ADC. One of the biggest things that I want to make sure when making this is that I keep the power away from the signal so that I don't add any noise to the system.
Here we have the DC to DC converter. First schematic iteration done in EagleCAD, in which shows the components that were needed and how they are connected to make a functioning DC to DC converter. The function of this PCB is simple. It is desired to convert higher or lower voltages to the desired voltage of the device. The current DC to DC converter design is to handle voltage minimums of 2.4 volts and a voltage maximum of 5 volts. The converter is also set to have a maximum efficiency of 88.1%. The DC to DC converter acts as the safety net for the device and helps the device perform as efficiently as possible. This is the continuation of the DC to DC converter layout, in which is showing the circuit's wiring layouts and how the PCB will be designed in EagleCAD.
Alright, back again to tell you about light emitting diodes. Now the main three things we looked at were brightness. We wanted something where everyone in the audience would be able to see it clearly. We looked at color spectrum because we wanted a wide variety of colors from each light. And we wanted longevity so that they wouldn't burn out and die too soon. Alright, so the two main types of lights we looked at for the project were the SMD lights, which stands for surface mounted diodes, and COB lights, which stands for chip on board. Now, there are three main things we looked at were brightness, energy efficiency, and color and temperature. The first thing we checked, we wanted something very bright so that everyone in the audience could see it. So we originally wanted to go with the COB because it has an 80 and up lumens per watt, lumens being the unit of measure for light brightness, whereas the SMD only had 50 to 100 lumens per watt. Next was energy efficiency. To help with the longevity of the lights, make sure they didn't burn out too soon. They were both highly efficient, so nothing really made much difference over there. But the most important thing on this chart that you want to look at is color and temperature. We needed something where we could change the colors at will. Unfortunately, only the SMD lights had that feature. COB lights were just one non-adjustable color, so we ended up using the SMD lights for our project.
When beginning this project, we looked into power supplies for powering the system, and the main factors in that were portability, cost, and life cycle. As you can see from the table here, we took in many factors. The size would be a big factor if we did want to go with a battery pack, because that would be adding weight and bulk to the system, especially if you wanted it to be portable. That would be an issue. The cost also, because each battery pack was at least double the price of what it would be to plug it in. And then we realized that we would already have to tether it to the microphone, so it really wasn't worth it to add a battery pack when there would still be wires tying it to something, and then you wouldn't have to recharge it.
Our device needed a display screen, in which has to be within the criteria of display size, resolution, compatibility, power consumption, and cost. The LCD display also has to be the best option in comparison to all the available displays on the market. Picking the best display, we compared to 3 different types: LCD standard, OLEDs, and QLED screens. The one we selected was the standard LCD screen, reasons being the best option at the lowest cost. The cost is $40 and the only downside is the resolution quality being 800 to 480p. However, it is being a smaller size of 5 inches long, compatible to the Raspberry Pi 4. Features include the touchscreen, which reduces the device complexity and size from the lack of physical buttons, and also only consumes 5 VDC of power. Again, the standard LCD screen was the best option for our design and budget. The design was done through SolidWorks under the need of having the device portable and organized. The design is a simple box design that has 2 cavities meant to hold the electronics. The design would be holding the LCD screen in the front, while the microcontroller converter's battery pack will be in the middle cavity and will be sealed by a back cover. The material that makes up the device frame will be PLA with screws connecting to each corner of the frame.
One of the main challenges of this project was converting our audio input into colors. We initially started off with a Python program that took in frequencies and assigned them to colors. We used this to test our components, however, it was not perfect. After we were approached by our sponsor to merge our project with our CS counterparts, we switched our programming language to JavaScript to better integrate our components with our MERN stack application. The basic idea behind how we will be assigning colors to music is illustrated in multiple levels, with the most simple of them being single note to color relationships. With this, we will assign all 12 notes in the chromatic scale to a specific color. Once that note is interpreted by the program, the respective color will then be displayed. For example, if we were to have the note A flat, we would then correspond it to the color blue. The next level of color assignment has to do with the relationship between notes being played. This plays off the previous level of assigning single notes to colors, however introduces variation in color based on intervals being played successfully. For example, if we were to play the note C, which is assigned to the color green, and then play the note G, which is assigned to the color blue, we would produce a color mix of both notes to create a teal color, which presents a note interval of a perfect fifth. The top level of color assignment is polyphonic sound. This level is the most complex to integrate and may be a bonus feature if the previous levels are completed on time. In this level, we would be able to differentiate the sound coming from multiple instruments. For example, if we had a trumpet and a flute playing, we may assign more aggressive and dark colors to the trumpet and brighter colors to the flute.
Alright, you thought you were done with me, but I'm back again to tell you about implementing the color schemes. Now, the color schemes were used to determine which specific notes get which specific colors, and we wanted to have the ability to add, edit, and delete new color schemes from the profile. So if you look at the image to the right over here, you'll see that each scheme has a customizable name, and each note from A, C sharp, F, B minor, D, F sharp, each one has a color next to it. You can click on those little boxes and you can select what color you want to apply to each note. And then when the microphone and the app pick up a sound emitting the frequency for that note, it will display that color on the lights. Alright, I'm sure everyone remembers Fourier transforms. This is basically the backbone of our project. It is what makes everything work properly. And a Fourier transform is basically an algorithm designed to interpret repeating patterns. It's typically applied in sound engineering, optical engineering, electrical engineering, computer engineering. We've all seen it. Sound in general can be defined as the fluctuation of air pressure over time, and the Fourier transform finds the frequency of these fluctuations and converts it into a list of frequencies. A note, a musical note, is a specific frequency range. For example, 120 to 150 would be, let's say, A. I don't remember off the top of my head. And most sounds are made up of several frequencies. Now, in our program, we use an application that uses the fft.js library to implement fast Fourier transforms, which is basically just an algorithm made for quick computer calculations. All right, work distribution. From the start, we had 2 software engineers and 2 hardware engineers. We had Anya working on the ADC. We had Stefan on the DC to DC converter. We had Music Man Carson working on music integration, and myself, Lath, on the RGB integration with the lights and instruments. All right, this is the last slide before you don't have to hear my voice anymore. Quick progress chart from bottom to top. Research and design are both almost done. However, our sponsor has us working with the CS team, and we're trying to merge our project with theirs. So a little bit of unexpected R&D that we need to do. Prototyping, we have our first successful prototype. We just need to add the PCB and the portability. Testing, we've successfully tested the microphone, the lights, the instruments, and the application. All those are working fine. We just need to complete our PCB and continue testing that. And the future section right there is for the portability, which we have not started building yet, but we'll hopefully get on pretty soon.
Like all projects, ours had a budget threshold that was given by our sponsor, Dr. Lineker, requesting that the cost does not exceed over $1,000. Currently, the device is projecting to be around $450, and which falls under the budget line. However, the completion of the device isn't done yet. More unexpected costs can arise. If the cost does go over budget, funding by the students might be needed and will be done accordingly. This is the demonstration of the device first prototype and how the input is being read by the microphone and microcontroller and then outputted through the LED strip. In future demonstrations, an instrument will be playing and all background noises will be successfully filtered out, leaving a very accurate output display from the LED strips, along with full usage of an LCD screen to manipulate the themes and brightness of the LED strips wanted by said users.
I thought we're doing like an abstract.